In this video, we're going to talk about the idea of hybridization as well as bond angles and some sort of shape that we should expect. So at the arrows, this is actually an naproxen, which is a COX-2 inhibitor, um, uh, marketed as a NSAID or non-steroidal anti-inflammatory drug. I'm pretty sure some of you guys are familiar with naproxen. And the idea is that at every, whether it's at A, B, C, D, E, we want to be able to tell the hybridization, the expected bond angle, and the shape. Right? So this is where we're kind of getting into organic chemistry. So if we look at A, well, remember, if we draw, remember in organic chemistry, we necessarily do not always draw our methyl groups or our hydrogens. But if we look at A, what we're really looking at is a double bonded carbon that has some sort of R group, right? And the R represents this portion of the molecule. But remember that even though we did not explicitly draw the hydrogen, there is a hydrogen at that point. So we say at A, the hybridization should be sp2. Why? Remember, we get one bond from the S, or in other words, one electron group from the S, so that's S1, p to the 2, so 1 plus 2 is 3, and in fact, we see 3 electron groups. Right? So remember, when we talk about hybridization, what we're looking at is electron groups. So that means that a double bond as well as a triple bond still counts as one electron group. A lone pair still counts as one electron group. Even a radical still counts as one electron group. Right? Now, for sp2, the typical bond angles are usually 120 degrees. Now, the shape of this is because, again, there are no lone pairs to modify the structure, so the shape of this is actually trigonal planar. And this is kind of bringing us back to general chemistry 1 or general chemistry 2. For B, what would you say the hybridization is? Well, what we're really looking at is a carbon that has an R group, and this is what our R prime is. It also has another R group, which is our R double prime. Right? Is there another bond? Yes, we do have another bond as R, I'm going to say 3 at this point, and this represents this bond. Now remember, to R2, there's a double bond here. Right? So the only thing I'm doing is just redrawing the structure of carbon B so we could actually see what is really going on. And again, we have 3 electron groups. This should be sp2. Typical bond angles for sp2 again is 120 degrees. And again, it's the same thing, 3 electron groups. We do not have any lone pair to possibly alter the electron geometry. And so we say the shape is still trigonal planar. How about C? Well, let's look at C. It's interesting that for C, and let's see if I could actually do it on this side. For C, carbon C, there is actually a CH3 at that point. Again, we do not explicitly write the CH3 because in organic chemistry we do not. But again, this is where it becomes a little bit difficult. You have to be able to realize that we have a CH3 at carbon C. We also have a CH3 at this junction. Right? So if we kind of redraw what we're looking at, we have a CH3. It means a carbon bonded to 3 hydrogens. And we also have this bond going to this carbon, right? So this wedge, or dash, I'm sorry, is also a bond. And we're going to label that as R prime. All right? So that means that we have 4 single bond around the carbon. This is typically your sp3. Again, S1, S to the first power, and the P to the 3 power. So 3 plus 1 is 4. And in fact, we actually do see 4 bonds around the carbon of interest. Right? Typical Sp3 bond angles, again, this would be 109.5, and we're looking at a tetrahedral here. Right? Tetrahedral shape, bond angles, usually 109.5. Again, there's no double bonds, there are no lone pairs to alter or tetrahedral structure, and so we say both the electron geometry and the molecular geometry would be tetrahedral. How about carbon? Well, in this case, it's an oxygen, but how about D? Well, I do see an oxygen. Now remember, our oxygen has no charges on it, and so if I represent this as the oxygen, and I have a double bonded oxygen. Remember, because there are no charges, oxygen has satisfied the octet rule. So even though we did not write the lone pairs on it, we should know at this point in organic chemistry that an oxygen with two double bonds has two pairs of lone pairs on it. Right? And so how many electron groups do we have around the oxygen? Well, we have 1, 2, 3. And so this is typically your sp2 hybridization. Again, 2 from P, 1 from S. 1 plus 2 is equal to 3. And we actually see 3 electron groups here. Now again, this is a trigonal planar. Right? So the shape is trigonal planar. And so we should expect to see 120 degrees with respect to the bond angles. And we're looking at trigonal planar. How about the last one, which is E? Well, I'm looking at an oxygen that's bonded to a hydrogen. It's also bonded to an R group, which we do not care about, or R group being this aspect that we represented as R. Now remember, this oxygen is neutrally charged. That means that it has to have at least 2 pairs of lone pairs on the oxygen. That's the only way it's going to be neutral. And so in this case, we have 1, 2, 3, 4 electron groups around the oxygen. So we're looking at sp3, 3 from the P, 1 from the S, 1 plus 3 is 4, and so that is our sp3. Now the shape of this is trigonal planar. I'm sorry, not trigonal planar, but tetrahedral, since we have 4 electron groups, going back to our general chemistry. And so we should expect the bond angles to be for tetrahedral, again, 109.5. Again, we're looking at a tetrahedral. Right? So this video is just to remind you of the idea of hybridization. Again, a couple quick examples. If I have, let's say I have CO2, right? And if I asked you about the hybridization, what would be the hybridization of this carbon? Right? And we say this carbon should be sp, right? I have s to the first power, p to the first power. I have 2 electron groups, right? Again, remember that one double bond still counts as 1 electron group. A triple bond still counts as 1 electron group. So it goes by the number of electron groups that is centered around the atom of interest.